Hey, everybody out there. Can you all see the warm-up?
Yep.
Okay. So go ahead and start with the warm-up. I'd like you to take matrix D and invert it by hand, where D is equal to 4, 7, 2, 6. And then I would like you to verify D inverse by hand and by calculator. Now, of course, you're writing this down on paper, so you can actually do it in whatever order you want. If I was you, I would take the matrix, input it into the calculator first, take its inverse by using your calculator first, so that you know what the correct answer is that you're working towards, and then prove that you can actually do this by hand. Full disclosure, D inverse is going to contain fractions. I highly recommend that you always work with matrices with non-integer values in fractions, never in decimals. And just like hot pro tip, this is a verifiable test question. This is a really, really good test question because it kind of has a bunch of different skills built into it. And when it comes to asking you to do this, to invert something by hand, I think inverting 3 by 3 by hand is way too time consuming to do in the context of a test. So if I ask you, when I ask you to invert by hand, it will be a 2 by 2 matrix. Are there any questions out there? Either on today's warm-up or the homework? Also, like, Happy Earth Day?
Mr. Robinson,
So,
are we taking notes today for a new section?
yeah.
The last section?
Yeah, today we're doing notes on the last section.
Is it about Cramer's rule?
It is about Cramer's rule, yeah. How do you know?
I looked at the section in the book. We kind of went over it last year.
Yeah, you usually do. Yeah, so that means that you guys have worked with determinants before?
Yeah.
Yeah. I guarantee today, I mean, just like any topic in math, the first time you learn it, you do like a brief overview, like how we did sine, cosine, tangent in geometry, and really all we took away from that was SOHCAHTOA. But after doing all that trig manipulation stuff this year, we found out that there's like a way deeper world to all of that stuff. The same is true of matrices. So last year in Algebra 2, y'all may have worked with determinants and Cramer's rule and all that stuff. But today, since it's the second time that you've seen this, what I actually want to talk about is like that deeper world. So what is some of the like fancy stuff that you need to know about determinants? And what are some of the applications where you'll see this stuff pop up, especially with a bunch of y'all smarties out there jumping a year and going straight to community college? I mean, not just because you're like a combination of being smart and also the school is closing senior year, so you find yourself in this situation. With all of y'all jumping to college real quick, I want to be big on this lecture about some of the applications in college where you'll see these matrices and these determinants. And keep in mind, the most important stuff to take away from this isn't even necessarily like the how-to, because to be honest with you, like given enough time, even I'll forget how to do a math procedure. That's why I'm going to be real big on vocab, so that if you need to look this stuff up, you know exactly what to Google. Let me take attendance and then we'll get rolling. Yeah.
Can we use determinants for 2 by 2s?
You can, yeah.
Do you mind?
Do I mind?
Yeah, like if we use them on the test instead of using using it with the identity matrix.
Oh, using determinants will not allow you to invert a matrix. Using determinants would allow you to solve a matrix. So if you had a system of linear equations like 3x plus 2y equals 5 and 6x plus 8y is equal to 9, determinants will let you solve for the ordered pair x and y. However, the way that this matrix is presented on the page right here, this has no solution because I'm not telling you what it's equal to. This is the same as saying 4x plus 7y, 2x plus 6y, but without giving you what constant they're equal to, you can't actually solve for where they intersect. coolio. Okay, let's go. Okay, so in order to take the inverse of this matrix by hand, who wants to tell me our general procedure? How do I start off finding an inverse by hand?
Set it equal to the identity matrix.
Yeah, we're going to go ahead and we're going to attach it to the identity matrix. I'd be careful about saying setting it equal, because that's not.
Yeah, sorry, that's not what I meant. Sorry.
Oh no need to be sorry. Like like everybody knows what you're saying when you say that. Just pointing out that it's like I won't fight you over it, but a math major might. The word equal has a real crazy strict definition, but yeah, the point is we're going to take it and we're going to stitch it to the identity matrix. You know, that's not even the technical term. I don't know what the technical term for you know, putting these two side by side. I'm not sure if there is a technical term for that. Nonetheless, we put this guy in the identity matrix side by side, and now we're going to do row operations until the left-hand side looks like the right, which is going to change the right side. And whenever we get on the right-hand side, that's going to end up being D inverse. So the first thing that I need to do is I need to eliminate this 2. And so I'm going to multiply this bottom row by -2 so that I can eliminate it with 4. So this is going to give me 4, 7, 1, 0, -4, -12, 0, -2. And now to row 2, I will add row 1, which is going to eliminate that bottom left-hand entry, giving me 4, 7, 1, 0. 0, 7 plus -12 will give us -5. 1 plus 0 will give us 1. 0 plus -2 will give us -2. And so I've eliminated this bottom left-hand corner. Now we have 5 and 7, and last I checked, 5 and 7 are both prime. So we're not going to get any common multiple, which is lower than just whatever their product is. So I'm going to take the top row and I'm going to multiply it by 5. I'm going to take the bottom row and I'm going to multiply it by 7 so that I can eliminate these values as 35. So the top row is going to become 20 and 35 and 5 and 0. The bottom row is going to become 0 and -35 and 7 and -10. And now this row added to the first row, so adding row 2 to row 1, is going to eliminate those 35s, giving me 20 and 0. 7 plus 5 is 12. -10 and 0 is -10. And the bottom row is unaffected, 0 and -35 and 7 and -10. This puts us one step away from the finish here. What do I do to make the left-hand side into the identity matrix?
Divide the top row by 1/20, or multiply it.
Yep.
And multiply the bottom row by 1/35.
Wonderful.
-35.
Yeah. And so when I do this, the whole point of that final step, that final op, is going to give us 1, 0, 0, 1, which is wonderful. And then in the row above, it's going to ask us to divide. And I'm going to go ahead and simplify these fractions as I go along, just so that I don't have to rewrite another line. So 12 divided by 20 would simplify to 6/10, which simplifies to 3/5. -10 over 20, that's -1/2. Wait, did I make a mistake? Wait,
No.
12/20, 6/10, 3/5. Yeah, okay.
Right.
And then 7 divided by -1/35, that's going to be -1/5. And then -10 over -35, both divisible by 5 and by that negative, so it'll end up being positive.
2/7.
2/7, yeah. 2/7. And so that means that this element here, these 4 terms, this should be D inverse. Is that first part, is that okay? Are there any questions on doing, getting an inverse of a matrix by the most manual method possible? No? Good? Okay.
Yep.
So now I'm going to go ahead and I'm going to do the stuff by calculator one more time, just because unlike, you know, the other stuff that your graphing calculator does, all of this stuff, even the act of entering a matrix, is buried within a ton of menus. And so I'm sorry if you're getting tired of it, but while I have you all captive and looking at a computer screen where it's really easy to show you the calculator emulator, we're going to run through this together. And so what I'm going to do is I'm going to hit second matrix, and I'm going to clear matrix A. Sorry, I'm going to edit matrix A so that it looks like my, so that it is matrix D from the problem. So we're going to turn this guy into a 2x2. We're going to enter 4 and 7, 2 and 6. And I'm going to quit out to the, I was about to say desktop, the top menu of the calculator. And I'm going to choose second matrix. We're going to pick matrix A. And then to make the calculator give us the inverse, just like our symbology, right? When a matrix is another matrix's inverse, we give it a -1 exponent. The same is true here. And go ahead and check those decimals. 3/5 is 0.6. Oh, I must have made a mistake. The top right entry is supposed to be 0.7, not 1/2. So we'll take a look back at our matrix for that. The bottom left entry is -0.2, which matches. That's 1/5. And then the bottom right entry is 2/7, which doesn't match. Did somebody see where I made a mistake? Or did I enter the matrix wrong in here? 4, 7, 2, 6. Huh. That's not good. Anybody? What happened? What happened? What happened? I guess I should have taken my own advice and done it in the calculator first. Go back where?
Yeah.
Mr. Robinson,
Mm-hmm.
wherever you wrote 0, -35, 7, -10, I think the -10 should be -14. Or did
Yeah, that's it. Yeah, 7 into -2 is definitely not -10. Dang it. Man. Okay. Boy, that's a bad sign. I have a midterm today, and if I'm making these types of sloppy errors this early, I should probably go for a run. Hey, anyway, yeah. So 7 into -2, that's -14. Which means that here, when we add row 2 to row 1, this is also -14, which is why both of those values are off. So that's -14. And then that means when we move into this next row, this is still a correct step of division, but what we get here in the right-hand column ends up being different. This is also -14. So then these fractions end up being -14 over 20, which will simplify to 7 over 10. Yeah, 7 over 10. -7 over 10.
And 2 over 5.
And then the bottom right-hand corner is 14 over -35, which ends up being positive. The 7 simplify out, yeah, into 2 over 5. And so I didn't make a mistake. I'm a teacher. We don't do that. Of course, this was to show you that if you have a calculator on a test, you might as well use it before you set out on doing a problem so that you know what the answer is that you're working towards, so it's easier to catch your mistakes. That's totally what I did, right, everybody? Yeah, that sounds good, Mr. Robinson.
Yeah.
Real smart. Totally. And so I will take this now as being verified by our calculator. So let's go ahead and verify it by hand. I'm not going to do it both ways. You have to. I won't, but you have to on the test. I'll be specific about that I want both D and D inverse. So we'll just do D into D inverse, D into D inverse, in order to show that this product is in fact the identity matrix. And so we have 4, 7, 2, 6. We're going to multiply this with 3/5, -7/10, -1/5, 2/5. And again, when we multiply two matrices, which is definitely a thing I'll be asking you to do on the test, and not just for the sake of doing this, but I'll also ask some other multiplication questions. We are multiplying the rows of the first matrix by the columns of the second matrix. And so entry 1, 1 here is going to be 4 times 3/5, which is 12/5, minus 7/5. And then our second entry here is going to be -28/10 plus sorry, plus 14/5. Our bottom left entry here is going to be 6/5 minus 6/5. And then our bottom right entry here is going to be this by that. So that's going to be -14/10 plus 12/5. And so you'll notice here that 12 minus 7, that's going to give us 5. 5 over 5 is 1. -28/10 plus 14/5, these are both actually the same fraction, right? Just multiplied by 2. If I multiply this by 2/2, this would give us 28/10. So -28/10 plus 28/10, that's 0. This one's more obviously 0, right? It's exactly the same, minus each other, 0. And then this one over here would be -14/10. To give this a common denominator, I'd have to multiply it by 2/2. This would give us 24/10. -14 plus 24 would give us 10/10, which is also 1. So even though it ends up with fractions, the multiplication of a matrix with its inverse will still yield back the identity matrix so long as you don't make the same algebraic error I did. Sorry, arithmetic error that I did.
Mr. Robinson, the second way to do it is you just flip. It's D inverse times D.
That is not a second way to do it. So that's actually mandatory in order to verify inverses. So I did this part, D times D inverse. You must also do D inverse times D. I'm also,
Okay.
or I'm only skipping it for the sake of time.
Yeah, okay.
Good. Okay. So today we're going to talk about our last section of notes. And just so y'all know, my current plan is to have the test next Tuesday. We'll see how well that holds. So tomorrow we're going to have a workshop on this section 9.8. And then I'll also talk about what's on the test, and then you'll have the whole weekend to work on the 9.8 and the review assignment. Monday will just be a chance to ask questions, nothing past that. And then Tuesday we'll have our test, or at least that's the plan for now. We'll see how lecture goes, but it won't be any earlier than Tuesday. Today we're going to talk about 9.8. Which I hear y'all have done before, which that sounds about right. I remember that from past classes saying that they had done it the year previous. But 9.8 is Cramer's rule. And all that Cramer's rule is Cramer's rule is a technique that allows us to solve for the solution to a system of linear equations by using determinants. So this lecture is actually going to not be about Cramer's rule until the very end. Because in order to give you the technique, what term am I going to have to very, very, very clearly define here?
Determinant.
Yeah, so Cramer's rule is actually about determinants for the whole first big chunk. Then after we have a very good definition for determinants, at the end, we will outline Cramer's rule. So I'm actually going to give the heading Cramer's rule again, oddly enough. And depending on how much stuff I say about determinants, we might not actually get to Cramer's rule today. So just keep that in mind that maybe this lecture doesn't have a punchline until tomorrow. So number one, what is a determinant? So a determinant I'm sorry, I shouldn't start the definition with is. Determinant is a single value determined from the values of a matrix which provides information about the character of that matrix. And I don't mean like character in the English sense, like, oh, this is the protagonist, he's the good guy or whatever. I mean that the determinant is going to give us information about the matrix and some of its properties, but exactly what that information is different based on what that matrix is meant to represent. Now, just so you know, we're going to talk about a couple different examples here, things that you'll see in the future, not so much in this class. But whenever you take a determinant, the way that this is written is that the determinant of a matrix A, you could write this, det, D-E-T, and this is the way that it's displayed in your graphing calculator. But the other way in which you'll see the determinant written in terms of nomenclature is if you see absolute values written around the outside of a matrix. Normally, an absolute value means to take all of this stuff and just make it positive. For reasons that y'all will learn later on in your mathematical careers, whenever the absolute value symbols, those like vertical lines, are used on a matrix, that means take its determinant. So here are some examples of the character of a matrix. So one really wild usage that you can use for the determinant is that if a system of linear equations has a determinant of 0, then that system of equations has no solution. If you take the determinant of a matrix and that determinant is 0, you cannot actually use that matrix in order to build or solve a system of linear equations. This is to say that if you were to, take a system, turn it into a matrix, take its determinant, if the determinant is 0, two of those lines are parallel, and as a result, you just can't solve that system. Here are some other examples of what the determinant can give us. And again, this is conditional on what the system is. Case 2 here. If we were to make a matrix, right, out of the corners of a triangle. So let's say it's geometry, and I have a triangle in the XY plane, and this guy has 3 corners. And these corners are ordered pairs such that it's A, comma B, C, comma D, and E, comma F. If you were to take these entries and put them into a matrix, which is to say I have A, B, C, D, E, F, and then I'm also going to fill out the right column here with 1, 1, 1, and then also take this guy's determinant, which we haven't talked about how to do yet. But if you do this for a triangle and then multiply this by 1/2, so 1/2 multiplied by the determinant of a matrix made of the corners of a triangle, guess what this gives us back? Where do you see the number 1/2 in the context of triangles?
Area.
Yeah, this literally gives us back the area of a triangle. Now, this is not a type of question that I'm going to ask you to solve. This is a thing that you'll definitely end up doing in college. If you end up taking anything called analytic geometry, or linear algebra, this is a common application, the fact that you can have a triangle in space and get its area by taking a determinant. Now you may ask why would you do this, right? When you just have 1/2 base times height. Well, maybe instead of the triangle sitting flat on the XY plane, it could be in space, stretched out in the up and down direction, in which case this would be a much easier way to solve for the area of the triangle rather than trying to use 1/2 base times height. Let me show you one more wacky application of the determinant, and then we'll finally talk about how to do it for some different size matrices. The third and final application of the determinant that I'll give you before we, finally take one, is that the determinant can calculate the volume of a parallelepiped inscribed by 3 vectors. So here's what this last one is talking about. A parallelepiped is just a 3-dimensional parallelogram. So let's go ahead and say that we're going to make our 3D parallelogram by drawing out 3 vectors. Vector 1, vector 2, and vector 3. And this first vector, and all of these for this to work out, they all have to start at the origin, 0, 0, 0. This first vector terminates at A, comma, B, comma, C. This third vector terminates at D, comma, E, comma, F. And this third vector terminates at G, comma, H, comma, I. And what I mean by parallelepiped is we would take these 3 vectors and we would use them to fill out a 3-dimensional parallelogram. Now, just so that we can see a computer-generated version of this instead of my potato hand drawing before I start, let me show you what this looks like produced by nice math drawing software. You take the 3 corners, in this case they're U, W, and V, and you copy all of them over to parallel corners to make kind of a slanted cube or a slanted rectangular prism. Does everybody see that? Am I sharing the correct screen?
Yeah.
Yeah. Visible. Okay. And here's why I show you that version, because the one that I just drew is horrible. It's horrible. I'm sorry. This is a crime. But I'll actually post the nice clean one to the Google Classroom so you can see it. This guy's volume is equal to the determinant of a matrix made of the entries A, B, C, D, E, F, G, H, I. So if you make a 3x3 matrix out of these 3 vectors, taking their determinant will give you the volume of the space on the inside of that 3D parallelogram. Now, like I said, the determinant has all sorts of wacky applications everywhere. There are even wild places in physics where, if you set up a column of electric field, you set up a column of magnetic field, you can take the determinant of that, and that will give you the magnetic flux. The determinant is useful in all sorts of ways. It's like saying, multiplication is useful. 4 kids have 3 candy bars each. Oh, they have 12 candy bars together. And the places that multiplication applies is enumerable. The same is true of the determinant. So here's how we actually take a determinant. So how to take determinants. So for a 2x2 matrix, it's pretty straightforward. Let's say that our 2x2 matrix is made of the entries A, B, C, D. If we were to take the determinant of this 2x2 matrix, then it's simply equal to AD minus BC. which is to say that we're going to take our first diagonal, these guys, we're going to multiply them, and then from that diagonal's product, we are going to subtract these two. So, for example, please take the determinant of the following matrix. 6, 4, 2, 3. And then over here, also take the determinant of 2, 8, 4, -1. I'm sorry. 2, 8, 1. Make that one positive. Oh no, my whiteout. Oh my God. Oh, it's ruined. I ruined my whiteout. I just broke my, oh. Oh, fixed it. Okay. Okay, so what are we getting for the determinant of this first entry here?
10.
I'm sorry, can you say that one more
Isn't
time?
it 6?
So this is going to be equal to 6 times 3 minus 2 times 4, which is going to be equal to 18 minus 8, which is equal to 10. So this first matrix here, this guy has a determinant of 10. This guy right here, let's go ahead and take its determinant. What are we getting out there?
0.
This guy's determinant is 0. So this is going to be equal to 2 times 4, which is 8, minus 8 times 1, which is also 8, which is 0. This
So
is
no
to
solution.
say that, yeah, this matrix right here, if this was written out as a system of linear equations, this would tell us that this matrix has no solution. And equivalently, it also has no inverse. And I think this is pretty quick and easy, even if we don't know what the right-hand side is, right? Let's say that we were to write this into a system of linear equations. We would get 2x plus 8y is equal to some constant, and we would get that x plus 4y is equal to some constant, where these two constants are different. If we were going to do elimination here, what would we multiply the bottom row by?
2.
-2, right?
-2, yeah.
So that would give us -2x minus 8y. And then when we add these two equations together, we would find that 0 is equal to some constant, which is what you get when systems of equations have no solution. A determinant of 0 means that a particular matrix has no solution and it has no inverse. Is this okay?
Yep.
Yep.
Okay. And
Mr. Robinson,
yes.
does that mean that before you find the inverse of a matrix, you have to find the determinant? So you know if you should keep working or not?
If you don't have a calculator on a test, yeah, that's a good strategy. Yeah, if you don't have a calculator and you're working with these types of 2x2 matrices, because once you like have this picture in your head like burned into it, right, you can inspect this and really quickly get the determinant. If you didn't have a calculator, I would say, yeah, that's valid. But if you have your TI-84, you might as well just ask it, right? Is that okay?
Yep. Yep.
Okay. And now here is one thing that we can do with the determinant for a 2x2, which is nifty. You know, I should actually draw a box around this because this is a definition. There's no escaping that. But let me show y'all an application of what we can do with the determinant of a 2x2 before we talk about taking the determinant of a 3x3. And I actually think we're going to have to push the test to next Wednesday. Sorry, because yeah, I'm definitely not going to get to Cramer's rule by the end of this period. We'll talk about Cramer's rule tomorrow after the warm-up. So I'll give y'all the homework for this section won't be due until Tuesday night.
Okay.
Okay, so another footnote here. Here is a shortcut for inverting a 2x2. Now, don't get me wrong, that thing where you take a matrix and you attach it to the inverse matrix and you do the row operations until the left-hand side becomes the identity matrix. That's what we did in the warm-up, right? I was like, hey, matrix A and matrix I, the identity matrix, and then we do a bunch of work, and when we're done, we have the identity matrix here, and now the right-hand side has become A inverse. Now, don't get me wrong, this always works. This will always let you find an inverse matrix should you need to calculate one, but you should know that there is a determinant-based shortcut for inverting a 2x2. And let me go ahead and show you what the shortcut is.
Mr. Robinson,
Yes?
on the test, do you mind if we do it this way instead?
I will give you specific instructions.
All
There
right.
will be a
Yeah,
case where
I
I
know
ask you to
this
use a
question.
shortcut, and then there will be another place where I ask you to do it the formal way, and I will be judging the work very critically. So here's the deal with the shortcut. If you want to take a matrix A, and let's say its entries are A, B, C, D, A inverse can be calculated immediately by the following shortcut. It's going to be 1 divided by the determinant of A multiplied by and here's how I think about these steps. We're going to take the entries on the diagonal and we're going to flip-flop them. So this is going to be D and this is going to be A. And then for the other two entries, they're going to stay put, but they're going to change sign. So this is going to be negative B and this is going to be negative C. Is that okay? So this is a straight up shortcut that will let us jump right to the inverse of a matrix in one step. So let's go ahead and do an example of this, and then we'll do the notes for doing the determinant of a 3x3. And let's go ahead and take the inverse of the following matrix. Let's say that we have the matrix D, and that's equal to 4, 7, 2, 6. Now, does this matrix look familiar?
The one from yesterday or a couple days ago?
On the
This is-
warm-up, right?
Yeah, this is the one from the warm-up.
The warm-up.
So, of course, I'm choosing this one because we already know what its answer is. We have the determinant from the warm-up itself. I'm sorry, the inverse from the warm-up itself. So let's go ahead and use this pattern in order to show that it gives the same answer, but in like one step instead of several. So the first thing that we have to do is we have to take the determinant of D, and that's going to be equal to 4 times 6 minus 2 times 7. 4 times 6 is 24, 2 times 7 is 14, and so our determinant is equal to 10. Is that okay?
Yeah.
Okay, so now that we
Wait,
know that
Mr. Robinson, why is there a long way to do this?
the long way is the correct way, this is a shortcut.
Oh,
The long way is the correct way, and the long way will work no matter what size matrix you have. So this method of finding the inverse, this right here, where you take the matrix, you attach it to the identity matrix, you can show that this is always going to be equal to that. So you actually use this to prove this, right? The same way how like you use completing the square to prove that the quadratic equation is correct, where the quadratic equation is just a shortcut. However, this shortcut only works for 2x2s. There is no equivalent shortcut for anything bigger. So if you need to find the inverse of a 3x3 or a 4x4, you must do it the formal way. Okay,
okay.
it's a good question. So that means D inverse is simply going to be equal to 1/10, because it's 1 divided by the determinant of that matrix. And then to get the other 4 entries, all I'm going to do is I'm going to swap the positions of the diagonal. So this is going to become 6 and 4, right? That is what it means to go from A and D here to D and A down here. And then for the other 2 entries, they're going to stay put, but they're going to become negative. So this is going to become -7. This is going to become -2. And then all I have to do is multiply in and simplify, and we get exactly the same answer that we got in the warm-up. 6/10, well, that's just 3/5. -7/10, well, that's just -7/10. -2/10, well, that's just -1/5. And 4/10, well, that's just 2/5. One and done.
Nice.
Mr.
Yeah,
Robinson,
it's great. It's lovely. Yeah. Yes?
if you leave it at that step where it's 1/10 and then the inverse matrix or whatever's inside the matrix, it's not completed, right? Like that won't be counted as full credit.
This and this are the same. They're exactly the same.
So you'll take that one too.
I would also take this. This is fine. My only point in getting from here to here is to show that it's exactly the same as what we got in the warm-up.
All right.
Also, on this topic, I said before that you could not invert a matrix if its determinant was 0, yeah? Go ahead and look at what role the determinant plays in this definition for the shortcut of inverting a 2 by 2. What would happen if the determinant was 0?
Divide by 0.
And can you do that?
No.
No.
So that's why I show you this technique. It's a good thing to remember that, well, if we want to invert a matrix by a shortcut, we're going to divide by some determinant, right? And the problem with that is that if the determinant is 0, 1 divided by 0 is not defined, and as a result, the inverse itself cannot be defined.
So would we just say no solution for the inverse as well?
Technically, you're not solving for an inverse, you're taking an inverse, so it would be no inverse.
Okay.
Good question. Okay, and now the last thing that we're going to do today is we are going to talk about the determinant of a 3 by 3. So under the heading taking determinants, this is item 2, the determinant of a 3 by 3 and larger. So this method that I'm going to talk about here that allows us to take the determinant of a 3 by 3 applies to a 3 by 3, but I'm sorry, give me 1 second.
Mr. Robinson, is this not Cramer's rule?
Well, so Cramer's rule is a rule that uses determinants, right?
Okay.
And when it comes to Cramer's rule, like built into the rule, it's going to be like, hey, it's the determinant of this divided by the determinant of this. So for any of that to make sense, the determinant has to be clearly defined, right?
Got you.
Yeah. Sorry, I'm looking up 2 words that I don't want to flip-flop real quick. The words being minors and cofactors. I just want to make sure that I have them straight and not backwards, because I don't want to give you all the wrong information. Okay, I got it. If you want to take the determinant of a 3 by 3 or larger, this is going to be a technique of cofactors and minors. And this is going to look wild because it is. So there's a couple different things that I'm going to do here, and you should know that this is the only way to take a determinant of a matrix, which is 4 by 4 or bigger. But let me just go ahead and again give you full disclosure. I have a dark and secret technique to tell you that there is a shortcut for a 3 by 3. A shortcut exists for a 3 by 3. And I will show that to you in case what I'm about to write down freaks you out. Let's go ahead and say that we are taking the determinant of a matrix of any given size. So we're going to do these notes with a 3 by 3, but I will also do an example tomorrow with a 4 by 4 so that you can see that it's still doable, right? And we're going to say that this matrix has entries A11, A12, A13, A21, A22, A23, A31, A32, A33. Whenever you see a matrix, you should know that the top left corner is positive. I'm not going to talk about why just yet, but know that that top left corner is positive. And from there, we are going to have a checkerboard of signs. So it's positive, negative, positive, negative, positive, negative, positive, negative, positive. And this pattern would hold no matter what size matrix you have. So if you're dealing with a 4x4, same pattern, 5x5, same pattern, 100,000 by 100,000, it's going to suck, but it is still the same pattern. Now, what I'm about to say is pedantic, so I won't bother writing it down. But if you needed to know the sign of one of these entries, what I'm actually doing is I'm adding these two numbers together, 1 plus 1. And if the sum of the indices is even, it's positive. 1 plus 2, that gives me back 3. If the sum of the indices is odd, then it's negative. This is just a pedantic way of taking these digits to reproduce this pattern. And so the way that we are going to take the determinant of this matrix, and I'm going to call this guy matrix A, is that the determinant of a large matrix, the determinant of A, is going to be equal to the sum, sigma, of all cofactors multiplied then by their associated minor. And here's what these two things are. A cofactor is going to be the constants in a row with sign considered, where the minor is going to be the determinant of the matrix that you get obtained by blocking that that cofactor's row and column. I know there's a lot going on here, right? Let me recap it before I show you like the formula here. The determinant of a larger matrix is going to be equal to the sum of cofactors multiplied by their associated minors. This is to say that you choose any row or column, and the weird thing is that the determinant that you get for a matrix, it's going to be exactly the same no matter how you do it. So we could go across row 1, row 2, row 3. We could even go down column 1, column 2, column 3. And what we're going to do in order to build this determinant is we are going to take this entry and we are going to multiply it by its associated sign. So this guy's positive, this guy's negative, and this guy's positive. And for each one of these entries, we are going to block out the row and the column of that entry. We're going to block out the row and the column of that entry, and we are going to take the determinant of the littler matrix that you get when that column and row are blocked out. We're going to go across one row or one column, and we are going to add up all of those digits. And so this is to say that one of the 9 different ways that I can define the determinant, I'm sorry, 6, because like I said, you get the same answer if you go this row, this row, this row, or this column, this column, this column. There are 6 ways to do this, but I'm going to do this in the traditional way. We are going to use row 1. This is to say that the determinant of matrix A could be calculated using the following pattern. It's going to be our first digit, A11. And is A11 a positive or a negative cofactor by our checkerboard over there?
Positive.
So this homie right here, that's positive. That's A11. And we're going to multiply this by the determinant of its minor matrix. So you want A11's minor? I'm going to block out row 1, and I'm going to block out column 1. And this 2 by 2 matrix that's left over, that is the matrix whose determinant I'm going to take. So it's going to be the determinant of A22, A23, A32, A33. And that is the first third of this determinant. We're going to have to do 2 more chunks of math in order to get the overall determinant here. Up next, we're going across this row. So now I'm going to take the cofactor A12. Is the cofactor A12 positive or negative?
Negative.
Negative, which is one of the trickiest parts about this definition, the fact that the signs alter. So now we are going to subtract, and just in case you look at these later, I'm going to highlight this minus. I'm also going to highlight this minus just to remind everybody that that's where it comes from, that some smart dudes came up with this definition. So it's going to be minus A12, then multiplied by the determinant of that entry's minor matrix. So I block out row 1, I block out column 2, and notice it only leaves available to us these 4 entries. That is our minor matrix. So it's going to be the determinant of A21, A23, A31, A33. And then finally, our final entry in row 1, I'm going to take cofactor A13, which is associated with a positive. So to these 2 terms, sorry I ran out of space, so I'll just put it in this line. We must now add A13 multiplied by the determinant of its minor matrix. So again, to get the minor of A13, I block out row 1 and I block out column 3. And I take the determinant of the 4 entries that are left over. The determinant of entries A21, A22, A31, A32. And again, like I said, this is one of 6 correct techniques. This is one of 6 correct approaches.
6?
6, yeah. So I would say that this is the approach that we get by going across row 1. However, the number that you get for the determinant for any given matrix is exactly the same, even if you go across row 2 or row 3, or column 1 or column 2 or column 3. The only difference is that here, where it was positive, negative, positive, if you went across this middle row, it would be negative, positive, negative. But as long as you observe these sign changes, the answer that you get in the end is exactly the same.
Oh, okay. So it's
yeah.
6 because you can do it to all rows or columns. It doesn't matter which row or column you take.
Yes.
That's 6.
Yeah.
Oh, okay.
Yeah. And the reason why I'm emphasizing the fact that you could do it any way you want is that depending on the matrix that you are looking at, there's a smart way to do it and there could be a dumb way to do it. And let me give you the hottest pro tip I could ever give you. Because, one time I got a correct answer on a math test at UCLA and it took me like 18 minutes. Because like I told y'all, I didn't learn matrices until I was in college. So it was really hard to learn this junk late. And then one kid next to me got full credit on the exact same question. It only took him like 4 seconds because he knew a trick that I didn't. The reason why I'm telling you when you do this, that you can choose any row or column, they all give back the exact same correct answer, is that if you want this to be easy, choose the row or column with the most zeros. Choose the row or column with the most zeros. It'll make it so that you get the correct answer in the least possible amount of work. Okay, so we're going to stop here for today. And like I said, this is very much not complete. This is not enough to do the homework, so I'm not even going to post it yet. If you're not done with the last section of homework, take the time to wrap it up and upload it tonight. Wait, it was due tonight anyway, right?
Yep.
Yeah, it's due today. Yeah.
Yeah, cool. I did plan this out right then. So yeah, take the time to wrap it up and get it uploaded tonight. And here's a quick inventory of what we will be doing tomorrow, just so that you know. I know this is a lot of stuff. And at the end of the section, I'll go over it one more time, which parts of this section you are responsible for and which parts of this section I included just because I think you're smart and I want you to see why we're bothering with this before you go to college. Here's what we're going to do tomorrow. We are going to do an example of the determinant of a 3 by 3. And we're going to look at one example with no zeros. And we're going to look at one example with a lot of zeros. The reason why we are going to do that is that you could take the determinant of a 10 by 10. It could take you days. It would be terrible. But if one of the rows was almost all zeros, you could do it really quick. There's a big difference in the work between these two sets. Then we're going to talk about the properties of determinants. The same way how we talk about multiplication is commutative, multiplication is associative, and those mathematical properties have ramifications, right? We are going to talk about the properties of determinants. What are some things that we can know about determinants? Like, how does the determinant change if I multiply a matrix or swap rows or whatever? Properties of determinants. And then finally, the last thing that we will talk about in our section is the title header, Cramer's rule. We will talk about how we use determinants and Cramer's rule in order to solve matrices. I know that this is a lot of real heavy stuff. Are there any questions?
Yeah.
No?
Mr. Rob, I have one question.
Yep.
About the negative sign. So can you explain like how we use that again? When we were subtracting the A11 and A12.
Yep. Yeah. So the checkerboard of signs, and like I said, what is actually generating this is you add up the indices, and if it's even, it's positive. If it's odd, it's negative. So 3 plus 3 is 6. 3 plus 2 is 5. Negative, positive for odds and evens. The only thing that these signs are doing, the reason why we're interested in this checkerboard, is the fact that as you go across and you take your cofactors, these signs will affect the cofactors. So A11 gets read out as positive because it's a positive entry. But when we get to A12, we're not going to add this next number. We're actually going to subtract it because the sign of its cofactor is negative.
Oh, okay.
Yep. That's why I highlighted them. Excellent. Okay.
Yeah,
We're a little bit over time, so tomorrow we'll end a little bit early since we went about 5 minutes over today. Tomorrow we'll end 5 minutes early. Y'all have a nice day. Finish 8.7, and tomorrow I'll assign 8.8. Take it easy.
Sounds
Bye.
good.
See ya.
Mr. Ross.
Thank you, Mr. Rob.
Bye.
Mm-hmm.